Welcome students. So in this video we are going to talk about double slit experiment and the classical and quantum aspect of this experiment, which is very important to understand the quantum nature or this wave particle duality that we have already talked about in the previous videos. To understand those phenomena, this double slit experiment is very important. So what is double slit? As you know that there is some two opening in a wall, very small opening, and behind that there is some kind of source is there. Source is kept behind that wall, and then we measure, then we place a screen on that, and we'll see what happens. Okay, we'll see what happens. So when suppose so the first case we send some bullets. We send some bullets through this. So this is, let's suppose, h1 hole 1, this is hole 2. So there are two cases. First case, it goes through the hole 1, the bullet goes through the hole 1. Then we will see a Gaussian like distribution of intensity of the bullet on the screen. Then second case is it goes through the hole 2. Then also we will see a Gaussian like intensity on the screen, corresponding screen. So in here, and if both the slits are open, then we will see a similar Gaussian like intensity, but little bit higher intensity this time. So what is the intensity was like I1 for first case, second case it is I2, and we find in the third case the intensity is nothing but I1 plus I2. So bullets are particles, purely classical particles. So for this the intensity simply adds up. Okay, simply adds up. Now we send a classical wave. Let's say we send some classical waves, means which have a amplitude and which has a phase. The phase is nothing but k dot r minus omega t. So this is a classical wave, and we are sending this through the same experiment, sending it through the same slits, like the same experiment. So the first case is going through, this is actually h1 plus h2 case. So the first case we find, so for this wave, if it is called psi, then we find for the hole 1, when the wave is passing through the hole 1, the intensity is psi 1 square for hole 1. When it passing through hole 2, the intensity is psi 2 square. And when it passing through both the holes, then we find that this is nothing but psi 1 plus psi 2 square. So interesting thing to notice here, so this is I1, this is I2, but this is not equal to I1 plus I2, not equal to I1 plus I2, because if we expand this we get psi 1 square plus psi 2 square plus 2 psi 1 psi 2 cos of delta. So I1 plus I2 plus 2 root over of I1 I2 cos delta. So we get some extra term, and so this is what we call as interference. So in the case of waves, the intensity directly doesn't add up. Instead, the waves individual amplitudes gets add up and then gets a square, and we get a extra term. So this term can be positive, negative, depending upon this cos delta, and in depending upon that we get constructive and we get destructive interference. depending upon this term. So this is clear. Now we'll look at the third case. Third case is we will send electrons through these holes. We will send electrons. So what will happen in the electrons case? For the first case, we see a similar Gaussian like distribution when it goes through the one hole. When it goes to the hole 2, we see a similar Gaussian like distribution. But when it goes through the hole 1 plus hole 2, passes through both the holes, then we see again interference. We see again interference. So this means what? This means electrons, which we know to be particle, is behaving like wave when we put behind the same experimental setup. So this is behaving as a wave, because otherwise we would not see an interference pattern here. So one interesting thing to notice here, so one thing in quantum mechanics, we know that measurement destroys the quantum state. So in the fourth case, what we will do the same experiment, but with a light source, keeping behind the wall, which light source will help us to observe the electrons. When the electrons passes through the hole, it interacts with our one of the photon, which also have a corpuscular nature, we already know, and it produces a flash passing through the when passing through the one of the holes, and it produces a flash. And we also put a Geiger-Müller counter on this screen, so that whenever the electron comes on the screen, we can hear a click sound. So it is measured whenever the electron is coming on the screen, it's measured. So the first case, it was uninterrupted electrons and we got an interference pattern. But interestingly, when we put a light source behind the wall and the light interacts with the electron, then we see even if both the holes are open, then also we get a Gaussian like distribution like the classical bullet. So when we are measuring, because measuring means some kind of interaction with the electron, so when we are sending the light source, so that such a way that when the electron passes through these walls, we get a flash, so that we want to understand when the electron is passing through the walls and when it is not. So how we will understand? By two cases, by a flash, which will be the interaction of electron and light source, and by a click in the Geiger-Müller counter. So we see in that case, there is no interference. So the interference is destroyed when the electrons is observed. So when it is observed, its quantum mechanical nature is destroyed and it behaves as if it is a classical particle, similar like a bullet. That is the thing. So next, what we think maybe our light source was very high, bright light source, that's why maybe it is disturbing. So we send a very dim light source. Even in that case, we see that we don't see the flashes. We see the flashes as much bright as before, but not the flashes all the time. So that means we miss some of the electrons, which is some of the electrons passing through the walls unmeasured, and some of the electrons is measured, and we collect both the distribution, and we see when it was measured, then there was no interference, and when it was not measured, it gives an interference. So it's that very bizarre nature of these electrons, that it is behaving as if it is a particle when it is measured. So this quantum mechanical property of the electrons is being destroyed when we are measured. So we can say So this electron behaving as a particle or as a wave is a completely quantum phenomena, because when you are measuring, it is destroying and it is behaving as if a classical particle. So this experiment proves the dual nature. This experiment proves the dual nature, the particle nature and the wave nature of our electron. Because both the natures we can understand, right? First is one is this light electron plus light source. This experiment proves the particle nature and only electrons. This proves the wave nature. So I hope this is clear, and we'll meet in the next video. Thank you.